So Pratap, I think I'll start.
Yes.
Okay. So welcome everyone to this second session of morning, parallel session 1. We have 4 speakers today, an exciting set of talks. I have been asked by the organizers to be very strict on time. So the speakers will get 25 minutes, 3 speakers will get 25 minutes, and I will give a warning 5 minutes before, and we will have about 5 minutes for question answers. So with that, I would like to invite Professor Yusuf to deliver his first talk of this session, which is revealing quantum behavior in a new class of systems. So Professor Yusuf, I invite you to come and deliver your talk.
Thank you, Professor Satyajit Banerjee. And I take this opportunity to thank the organizers, particularly TIFR and Professor Pratap Rai Chaudhary and others for giving this opportunity and first of all organizing this conference year after year. And this is what is helping for the growth of the science in this country in the area of quantum matters and quantum phenomena.
So
sorry
with this, will you be able to switch on your video?
Yeah, am I audible?
Perfect.
Yeah. So title of my presentation is Revealing Quantum Behavior in CaNi3P4O14, Na2CO2TO6, Na2Cu3G4O12, and Cu3CO3O2 base system. See, I have listed 4 compounds. Basically, we have worked on these compounds over last couple of years. And the point which I will be trying to make today is that the quantum behavior, it is so versatile. And with regard to this system, I'll be making a point that while the magnetic lattice is having low dimension, I mean 1D or 2D, then the quantum effects are more prominent. But of course, throughout the journey, you will also see that not all 4 compounds, they do see the very clear-cut quantum behavior. There are some cases you see the quantum effect is there, but marginally, in some cases, it is more stronger. So I'll be making these points from my presentation. Now, as you know, that if you deal with spin half chain with a nearest neighbor antiferromagnetic exchange interaction, and if for negligible anisotropy and interchain interactions, the ground state remains magnetically disordered even at 0 Kelvin. This is known. And if we, instead of 1D chain, if we talk about the 2D lattice, for example, the square lattice with magnetic spins at the corner of this 4 corners and with exchange interaction J1 and J2. J1 is first nearest neighbor and J2 is the second nearest neighbor, where the Hamiltonian is written here with respect to J1 and J2. And if you deal with the spin half system, for example, if you take copper, in fact, if you notice, all my compounds except one, everywhere I have taken copper is one the magnetic element in those 4 compounds which I already listed. Now, this is the phase diagram, theoretical phase diagram given, and depending upon the ratio of J2 by J1, either the second exchange interaction, second neighbor interaction to the first neighbor interaction, the ratio depends what kind of magnetic ground state you get. Obviously, when the J2, the second nearest neighbor is 0, that means only first nearest neighbor with antiferromagnetic exchange interaction, you get the conventional nil type of antiferromagnet. But the point is, when they are J2 by J1 about 0.5, then you see the quantum phase, that is the spin liquid phase. And if we go for higher strength of J2, of course, again, it comes back to the collinear antiferromagnetic structure. So that means this is the relative strength of these 2 exchange interactions. In a case of square lattice, it really matters what kind of magnetic phase you are going to see. And the quantum, the spin liquid, what I just talked about, I must tell you that in order to see this quantum spin liquid behavior, the ingredients what one would look for is what one should have in a system is that a very small spin value. And very small means the lowest value is spin equal to half. That's why out of 4 systems, all 3 compounds, what I have listed, you get the copper and copper 2+, and where spin is half. And another ingredient what you should have in order to see this quantum behavior, particular spin liquid, is a low dimensionality. Low dimensionality of the arrangements of magnetic atoms. And third is the geometrical frustration. All are the ingredients for observing this kind of quantum behavior. We have worked on this kind of system over the last more than 10 years, and wanted to set the background for this topic. I'll not be, of course, giving a review, but 1 or 2 examples I will be just showing. For example, this is the square lattice by the J1 and J2, which I just talked about. In this case, though, crystallographically, it is a 3-dimensional lattice. As you see, this is the unit cell. But if you look at this copper plane, where the copper spin up, it is forming the square lattice. So as far as magnetism is concerned, it is the copper spin up, and these copper 2 planes, they are the green. Here bromine is green and blue is the copper, and they are well separated, so that these 2D layers, they are can be treated as a 2D system, because these copper layers are magnetically almost not coupled because of the large separation in this. And we have worked so this kind of system. We have also worked the 1-dimensional spin chain kind of system, where these magnetic atoms, they form a triangular lattice. That means here you see the magnetic atoms are along the c-axis, but when you see in the AB plane, they form a triangular lattice. We have also worked on this. So this is just I'm trying to tell you that crystallographically, though we have dealt with the 3D system, but as far as magnetic lattice is concerned, that can have really lower dimension. So not necessarily that you have to make artificial low dimensional magnetic lattice all the time. Even in 3-dimensional system, you can look for it. And we have worked on this kind of system. A little earlier, this also the Haldane chain compound we have worked on, and here we have given the quantum phase transition from a spin liquid to spin glass state in this nickel-based system. Here you see these chains; they are the screw type of chains, and here we referred the papers of Nobel laureate Haldane, of course, before he got the Nobel Prize. So this is much relevant for this quantum phase transition. Now, before giving for today's talk the 4 compounds which I have already listed, let me give a brief background that when you talk about the chain system, a magnetic chain system, it can have a uniform chain. If there is only one kind of X interaction, that is J1, you can have dimer. If there is J1 and J2, you can have trimer, where J1, J1, and J2. This is the X interaction, magnetic X interactions I am talking about. So I'll be giving example of a trimer spin system just after this. This is a trimer spin system. As you can see, the crystal structure which has been derived by doing the Neutron diffraction experiment and analysis. And of course, the magnetic atoms here, there are 2 magnetic sites, nickel 1 and nickel 2. And basically it is J1, J2 kind of interaction along the chain. And the question here would be that what is the interchain X interaction? Throughout the journey, I will show that in fact, for this system, the J3, which is coupling between 2 chains, are not negligible, and that's why it almost shows like a 3D kind of behavior. Here we are talking about nickel 2+ and 3D state with spin equal to 1 and nickel 2+, and with the spin 1 trimer chain we are talking about. Now we have solved also magnetic structure, as you see here, how the magnetic moments of these 2 nickel inequivalent crystallographically 2 nickel sites, that is nickel 1 and nickel 2, how they are coupled, as you see here. And see, this is essentially, as you see, this is 1 chain, this is the 2nd chain, and this is 3rd chain, and this is what in this ellipsoid, what is shown here, 1 trimer involving J1 and J2 X interaction. So timers are shown, and essentially it is the exchange interaction between two chains, we'll see that from inelastic neutron scattering experiment that is antiferromagnetic, but along the chain it is almost like a parallel, but not perfectly. There is a canted. So canted ferromagnetic along the chain. That means it is positive X interaction, but not fully ferromagnetic. So this is what is the outcome by doing the neutron diffraction experiment. And see, we have also done this so-called critical exponent study. What is plotted here, the ordered moment at the nickel side, because in this case, nickel is only magnetically ordered, Bohr magneton per nickel ion, and as a function of temperature, this is derived from the neutron diffraction experiment as a function of temperature, and this is the paramagnetic state. So order moment is 0, but when the magnetic phase transition takes place, the growth of this side magnetic moment, and as I told you, there are two nickel sides, crystallographically inequivalent nickel side, nickel 1 and nickel 2, and both nickel sides moments are plotted here, and the Tn, the antiferromagnetic nil temperature, is found to be 15.992 Kelvin, and we have also done the critical exponent study and how this spontaneous magnetization, the ordered moment, it builds up as soon as the magnetic phase transition takes place, and with the critical exponent beta is found to be 0.36. And this is and what is shown here, that both nickel 1 and nickel 2, it is almost approaching the full value as expected from spin 1 system. Now we have also carried forward and then done the inelastic neutron scattering. This was of course done at ISIS. The first experiment was done in BARC using Dhuba, but this experiment was done at ISIS. And here, what you see here, that at 18 Kelvin, which is above the nil temperature, but below, when you go this below the magnetic ordering temperature 4K, you see the excitations. And without going to details, I will only say that there is a energy gap, and as a function of temperature, this gap is increasing, and below this TC of 16 Kelvin. And we have determined the exchange constants. That is what I was telling you, that to form the trimer J1 and J2, but taking this kind of Hamiltonian, that is J1 is the intrachain, means along the chain, and J2 is also along the chain, which are responsible for formation of the trimers. And you see both J1 and J2 are ferromagnetic. That's why you are getting almost a parallel kind of spin configuration. But between two chains, the strength is given by J3, and J3 you see the antiferromagnetic here, and that this strength is almost comparable to intrachain J1 and J2. So as a result of that, that's why it is behaving almost like a 3D system, though you do see the chain-like structures, spin trimers, and so on. Now I come to the second example, which we had. We have studied the exotic quantum behavior of spin half Kagome frustrated lattice. Here we are dealing with spin S equal to half, and it is a Kagome lattice. So copper, these are the copper, and copper is forming a Kagome lattice, because you see this is triangle, this is another triangle, but this is the corner shared these triangles, and it is the Kagome lattice, beautiful Kagome lattice. And yeah, this is what so copper involving spin half we are talking about. Now what is shown here, the DC susceptibility inverse as a function of temperature, and what you see here, that this theta Q device temperature is quite large, minus 68.3 Kelvin. But what we show on the next, but there is no magnetic phase transition. In fact, the specific heat as a function of temperature, by the way, this specific heat down to 86 millikelvin was carried out in collaboration with Professor Dhar, and we used TIFR facility. And so the specific heat down to 86 millikelvin, what you see, though there is 88% entropy is released down to 86 millikelvin, but there is no magnetic ordering. Now the question is, only 12% entropy is remaining if it has to undergo any magnetic ordering below 86 millikelvin, which is very unusual. So this is for the non-magnetic counterpart zinc, and this is the net magnetic, and this is the entropy calculation. Now we have also done the neutron diffraction experiment to confirm that indeed there is no magnetic ordering, and you see the difference pattern of the intensity of neutron diffraction pattern 1.5 and 25 difference pattern, which tells you the perfectly flat. So that means there is no magnetic ordering at all. That is very much confirmed. In fact, susceptibility, AC susceptibility plots are shown here as a function of temperature at different DC applied field and different varying frequencies. From this, we do not see any shift, and it confirms that there is, in fact, there is no spin glass ordering. There is no magnetic domain wall pinning. Otherwise, we should have seen the shifted behavior. So that means this transition actually is nothing but this kind of the transition from this high temperature paramagnetic to spin liquid kind of phase. But of course, I have not shown here under DC applied DC magnetic field, it is going to the field induced ferromagnetic state. And what I have plotted here in the phase diagram, and this is the QD temperature, where under very low field, even 200 field, Western field is enough to have the ferromagnetic state in this system. Now I go to the another system, that is again this is the cobalt based system, and in this case my intention is to raise a point that can we have the Kiteb spin model in this system, because so far, as you know, it has been talked about 4D 5D kind of system, iridium and so on, but in 3D tensor metal is it possible? And as you know, this Kiteb model when you talk about the Hamiltonian, this exchange is bond dependent, and that is what. So it is whether it is in X, whether Y, or whether Z, it depends. The extent depends upon that. And there is a pure model for Kiteb model, but I mean, there is in the literature there is a strong search for Kiteb, which the compound which satisfy the Kiteb model criteria. And there are reports, for example, on Na2IRO3, her iridium magnetism comes into picture, but it is very difficult to get a system which fulfills this Kiteb criteria, and that's why the theory also developed that along with the Kiteb, that K X interaction, if you have the Heisenberg, that a mixed one, Kiteb as well as K as well as J, both are there, then your Hamiltonian goes like this. It is not perfectly Kiteb, that is K S I S J, but you have also Heisenberg term, that is J S I dot S J, and in this scenario, how the phase diagram goes. See, if J is 0, that means no Heisenberg term, the pure Kiteb, then you get the spin liquid, okay? But when you have the KJ model, depending upon the strength of J and K, the theoretical phase diagram is given, and our system, which we are talking about here today, is basically we are dealing with cobalt 2+. And as you know, in 4D and 5D elements, for example, iridium 4+ and ruthenium 3+, you J equal to half, that is the ground state, and that gives the ingredient for the very low spin state, and it is ingredient requirement for the Kiteb model. But question is, 3D system, for example, cobalt 2+, recently, I mean 2018, in this paper, Khaliluddin et al., they showed that indeed cobalt 3D system, that is cobalt 2+, under the spin orbit interaction, can also have effectively J effective equal to half system, J half system. And with this, after this literature report, we thought, let us adventure into this kind of system, this cobalt 2+, in this Na2CO2 TeO6 system, where this cobalt is forming the honeycomb lattice, because this is another ingredient. So honeycomb lattice with cobalt 2+. So this is a potential system for Kiteb kind of phase. Now, this is the crystal structure we have determined, and magnetic structure also we have determined. So here all this cobalt, there are two cristographically inequivalent cobalt sites, cobalt 1 and cobalt 2, but forming a honeycomb lattice. And so it has, and if it behaves, cobalt 2 plus behaves as effective J half system, and then it is expected to satisfy this bond dependent exchange and so on. And this is our magnetic structure at the ground state, the frustrated honeycomb magnetic lattice, which is shown here, and it has been derived by doing powerful neutron diffraction data. And what I like to point out that we have seen in this case, even at 1.5 Kelvin, the cobalt at both the sides, the moment is reduced because S equal to 3/2. So with respect to 3 Bohr magneton, moment is reduced, and so that means even in order system we see some kind of effect of this frustration. Now, so as I told you in the previous view graph, this structure is the zigzag long-range antiferromagnetic ground state. That is what, and if you put that in this phase diagram, in this KJ model, our system falls here. That is a zigzag antiferromagnetic state. So it is not pure spin liquid, but it is very close to that. So it only means that K effectively K is there, but J cannot be neglected at all. That is what is the system of this. We have also extended this.
Professor Yusuf, you have 5 minutes.
Yeah, sure. We have also done this study by doing this single crystal study and the magnetization as a function of magnetic field by applying magnetic field both parallel to A and parallel to C. And this is the phase diagram. This is the phase diagram. Magnetic field as a function of temperature we have drawn, and this is the zigzag antiferromagnetic state which you just talked about. But under field, it is going to a state which, if we compare with the theoretical work, which is there in the literature, temperature as a function of field. This is the zigzag state which you are, but quantum spin liquid state is expected to go at higher field. So whether it is a quantum spin liquid state or not, that is what is our investigation at this moment. We have also done the inelastic neutron study, and here if J equal to half state under the trigonal compression, this is the crystal field state, and when magnetic ordering takes place, which indeed occurs for this system, again there is a splitting and there are 3 lines. So what I am showing here by inelastic neutron scattering study at 40 Kelvin, we see this crystal field line, only this red one, which is this red one. And but when magnetic ordering takes place, so if we do inelastic study at 4 Kelvin, so we do see these all 3 transitions, which is shown by this all 3. There is a 1-to-1 color coding, green, blue, and magenta for these 3 transition lines. These 3 all are crystal field excitations. We have also done a low temperature, that is, we have seen that is a spin wave, and we have done this, taken this kind of Hamiltonian, done the modeling, and determined the values of J1, J2, J3. And you see the K term is very much there, 3.5, cannot be neglected. So this is what, so that means from this we can conclude that both Heisenberg as well as Kitev interactions are very much present with this cobalt 2 plus, which forms the honeycomb lattice, and it is close to J equal to half ground state. This is the last example, just 2 slides only. This is another system we have been working on. I'll just give a glimpse of that. It is copper-based system, and here you see again the spin trimer, copper spin half spin trimer, and J1, J2, J3 interaction, and see J1, J2, J3, like what I discussed in the previous example with respect to nickel. So J1, J2, here what we have seen, this is the formation of trimer, and our analysis shows there is a possibility of J3, this kind of exchange interaction. And but between, now question is whether 2 trimers they interact, and that is what. And I will only show that this system shows magnetization as a function of field. There is a clear-cut 1/3 magnetization play to, and see at what field it. This is in Tesla. at what field we had to, this is the VSM data or PPMS data. Then we had to do the high field experiment in Germany. And you see this one-third magnetism Plato and the theoretical work which you have done with Manoranjan from SN Bose, and you see the beautiful representation of this one-third Plato, and of course there is a field-induced saturation. It occurs at nearly 300 Tesla. So this paper will be coming up. So with this, let me acknowledge all my collaborators, Dr. Anup Bera, who will be also speaking after one talk or so. Another, my colleague Anil Jain. And then, as I said, Pacific Heat study for one of the system was done in collaboration with Professor Dhar. This copper system, where we have seen the quantum spin liquid, that sample was prepared in Professor Tapos Maji's JNCSR lab. Kajali Ghosh, she also the first sample, the nickel-based sample was given by that, and inelastic neutron scattering, which was studied at ICIS UK by Dr. D.T. Azroja, is our local contact. So with this, I thank all of you for your kind attention.
Okay, thank you, Professor Yusuf, for a very nice and interesting talk. And the session, this talk is open for questions from the audience. We have time for a few questions. Okay, let me begin. I would like to ask a question. Okay, there is a question from Manoranjan. Yeah, go ahead.
Yeah, I'm just wondering about. Thank you very much for a nice talk. I'm just wondering about this spin 1 trimers. So, is there a way to synthesize, or do you know any compound which have the antiferromagnetic coupling? So here your J1 and J2 were like ferromagnet.
Yeah.
But it is the antiferromagnet that will be very interesting compound.
Yeah, in fact, is a very valid point. That is what we thought of getting, but we didn't get. See, I would say the best way to do that is playing with the bond distance between between two magnetic sites. So if you can play with the bond distance, as you know, the exchange, the interaction can change the sign from positive to negative. That means we have to work on the substitution, suitable type of chemical substitution, which might give you. Here, the pressure or any external perturbation like pressure will not be very effective because compressibility is not that high. So this is the one way probably we can get a system where J1, J2 could be made negative.
Okay. Thank you very much.
Thank you.
Okay. I had a question that in your cobalt system, you said that in the Kitaev spin, along with this Kitaev term, there is also this Heisenberg-like term, but that would lead to ordering. So would it not would you get a spin liquid phase, or I mean, that would be difficult to get?
Yeah. So you have raised a valid point. That's why I could show that from the neutron diffraction experiment, we are getting the magnetically ordered state.
Okay.
I mean, so we are not getting the so-called spin liquid. So we have not got because of this same reason.
Term. Okay.
What we could show, but what we could show that it is not pure Heisenberg. Definitely, K term is definitely there, and that's why the phase diagram with a Kitaev exchange as well as Heisenberg exchange and the zigzag kind of antiferromagnetic state that comes when you take both the interaction. So this is a system. It is a mixed exchange kind of. Both terms are present, but it is not purely Heisenberg. That is the point I was trying to make. In fact, as you know, literature, it is the challenge how to get a pure system which will have all the ingredients for Kitaev, and you will get the pure Kitaev kind of ground state. That is what is the search in the literature.
Yes, very interesting. We have time for just one. If it can be answered quickly, then there is a question in the chat box is from Monica Javale. is the compound Na2CO2TeO6 copper in the 3D transition metal where SOC is weak. Still, we are considering SOC to get spin orbit coupling to get J effective equal to half. So they are saying that in this compound,
you are talking about the cobalt system.
The cobalt system, right?
I mean, this is yet another important point. See, we have not, of course, done any theoretical calculation. I mean, that can be carried out with that kind of spin orbit exchange coupling. Either J equal to half, it is expected. But what I showed you that at the follow-up of this Khaliluddin's paper, that indeed in a 3D system with cobalt, one can look for this kind of Kiteb kind of ground state, and whether any effect is there. That is what we point. But whether that kind of, if it needs more theoretical attention, whether that kind of spin orbit coupling, how good it is to bring it. And I must tell you that since spin orbit coupling, as rightly pointed out, is weak, that's why its system is not purely K-type. It is more J-type and less K-type.
K-type. Okay.
But it is there.
Okay.
And
okay.
I will say that this has opened up the chapter that in fact 3D systems are also could be good systems from the theoretical paper and followed by our experimental paper to look for Kiteb kind of ground state. This is the new piece of information I can claim.
Okay, this is very interesting. I think we have run out of time, so let's thank Professor Yusuf for a very nice talk, and we move on to the next speaker. The next speaker in the session is Professor Pintu. So I would request him to keep time, and you can switch on your video. Yes, yeah. And can you share your screen? So I will warn you 5 minutes before the talk. 5 minutes before your talk ends.
Okay.
Yeah. Professor Yusuf, can you stop sharing? Yes. Yeah.
So is my screen visible?
Absolutely. Yes. It's somehow coming a little small. I mean, yeah. Yeah. Now it is fine.
Okay. Okay. Good afternoon, everybody. Thank you, Professor Banerjee, for the kind introduction. So I'm Pintu Das from Department of Physics at Indian Institute of Technology, Delhi. So the title of my talk is Charge Carrier Dynamics in Chiral Magnets with Strong Dzyalloshinskii-Moriya Interaction. So what I'll be talking about mainly is some fluctuation spectroscopy studies that we have performed recently, very recently, in materials which are hosting magnetic skyrmions. So this is my first talk in this QMAT conference. So let me thank the organizers for putting up a beautiful program and also for inviting me for this talk. Since this is the first talk, I'd just like to give a brief introduction about what we are doing in our group. So we are working in the nanomagnetic aspects, focusing on artificial spin ice, magnetic skyrmions, and also we are devoting some of our time to some developmental activities, making some high sensitive magnetic Hall sensors. So this is the broad outline of my talk. So I'll be talking about two different aspects. Of course, the title is about the dynamics, charge carrier dynamics. Dynamics, I mean, we'll be talking about low frequency dynamics, basically. So that is my second part of the talk. At the beginning, I'll give a brief information about our recent studies which we have performed to understand switching behavior of dipolar coupled nanomagnets using two-dimensional electron gas-based micro-Hall magnetometry. So these are the two different topics that I'll be covering in the next few minutes. Let me first acknowledge the collaborators. So from CNRS Thalys Research Lab, Vincent Cross group. So we are working together on skyrmions, and for the artificial spin ice system, we work together with Toyo University and Tohoku University in Japan. Japan. So these are the main work that I'll be talking about today. And these are my PhD students. So Niti Keshwani, who mainly worked on the artificial spin ice systems, and Hurmul Saran and Yogesh, they are working on the Skyrmion project. Okay, so so just to give you a brief introduction about the first part. So I'm not talking about artificial spin ice, but I'm showing you this slide just to just to show you that these nanomagnets, individual nanomagnets of highly shape anisotropy, they are used in studies of artificial spin ice or in different magnetic logic devices, neuromorphic computing, etc. So in all these aspects, the switching behavior of these nanomagnets are very important. Now, if you want to study this switching behavior, now, if you perform, let's say, global magnetization, for example, so what you see here on the screen is a large number of square artificial spin ice vortices. And if you perform global magnetization measurement, you typically see these kind of hysteresis loops. Of course, they are related to the switchings of the individual shape anisotropic nanomagnets, but you cannot get any proper information regarding the switching behavior. So if you, this is the same story. If you have, what I've shown here you earlier is the unconnected vortices. Unconnected means, I mean, non-interacting vortices, and even this is similar even for interacting vortices. So you do not get much information about the switching behavior. Now, if you want to understand switching behavior, you need to actually probe the individual magnets, nanomagnets. And since these nanomagnets are very tiny, you need very high sensitive tool to detect, to sense their magnetization. So now, if you typically in experiments, what you do is you perform imaging using, for example, in a typical lab, you will have a magnetic force microscopy. And here I show you a few nanomagnets, 9 nanomagnets. Topography is shown by atomic force microscopy images, and the corresponding magnetic force microscopy images show that they are very nicely single domain. They show single domain character. Okay, so so that means that there will be switching between the bistable states. This is what one actually observes in the magnetic force microscopy. Now, in order to understand this in details, you need high sensitive tool, as I mentioned. So what we have done is we have used two-dimensional electron gas in the heterostructure of 3,5 semiconductors, namely gallium arsenide, aluminum gallium arsenide. We get these wafers from a collaboration with Professor Hideo Ono in Tokyo University and in Sendai. So we pattern them in the Hall struct geometry. So we make Hall devices out of this, and then we use them to measure the stray field coming out of the nanomagnets. So what we do is we pattern nanomagnets on top of that. So these are wet etching, therefore the device doesn't look that nice. But it works nicely for us. So you see that these are the 9 nanomagnets which have been patterned on top of the whole device to understand the switching behavior of these dipolar coupled nanomagnets. So please remember that we are not measuring any magnetization. We are measuring the stray field coming out of the nanomagnets and reaching the two-dimensional electron gas, which is around 230 nanometer down the surface. And so what we are doing is we are measuring actually Hall voltage due to the stray field, Hall voltage of the 2DAG. And from the Hall voltage, we are detecting the magnetic signal. So we characterize them. These measurements were done at Professor Dasgupta's lab in IIT Bombay. I didn't have a measurement equipment here at IIT Delhi at that time. So, so these are the quantum Hall effect measurements and normal resistivity, longitudinal resistivity measurements of this device to characterize them. And what I want you to look at is the mobility of this material. So this is around 4 × 10⁵ centimeters square per volt second at around 1 Kelvin. So this is pretty high mobility, and this is very important for this kind of highly sensitive magnetic detection system. So we have performed the studies or performed the measurements in the ballistic transport regime. So the mean free path is about 3.3 micrometer, and the whole device size is about is 1 micron dimension. So we are in the ballistic transport regime. So what you see here is that this is the MFM image of the 9 nanomagnets that I have shown, and these are the Hall voltage actually if you remove the background. So this is the Hall voltage that you measure. So we see a very nice hysteresis loop, and on top of the hysteresis loop you see a very nice rich features on top of the hysteresis loop, which obviously you don't see in the global measurements. Now, to understand that, so these are the stray field which we have measured, as I said, and in the Hall voltage. And if you see that the entire signal is just less than 1.5 microvolt kind of signal. So now to understand that, because we are not averaging the signal, it is straightforward to compare them with the theoretical modeling. So what we have done is we have performed micromagnetic simulations using OOMF. And on the left, you see that this black is the experimental result, and red is the simulation results, where you see that the simulation result is almost perfectly matching. Features are almost perfectly matching with the experimental data, and these features show that the single domain character which we observed in the MFM. We really don't see a bistable kind of state. We see in between multiple other kind of complicated states, for example, in some cases vortex states, etc. And all these are picked up by our Hall device, our highly sensitive Hall device. So I'm not going too much into details. This is just to tell you that these very minor features that are observed in our measurements are related to some kind of magnetic behavior of the nanomagnets during switching. Okay, so these are a few of the examples here are at different magnetic fields, where you see that there are vortex charge structures, and corresponding to these, there are features in the simulation results as well as the experimental result. So I think this is in brief that I wanted to mention, that this two-dimensional electron gas based micro-Hall magnetometry is a relevant tool for very high sensitive magnetic measurements. And we have used this technique to study complex switching behavior in single domain nanostructures. So with this I switch gear, and I'd like to talk about the main topic of my presentation today, which is the charge carrier dynamics in chiral magnets. And particularly I'll be talking about magnets which host skyrmions, magnetic skyrmions. So as you know, for magnetic skyrmions, in the magnetic skyrmions, these are topologically protected spin structure for which Dzyalloshinskii-Moriya interaction given by this Hamiltonian is important. So this introduces the chirality of this chirality in this kind of spin systems. This Dzyalloshinskii-Moriya interaction, in addition to the Heisenberg exchange interaction, this leads to the chirality. So there are two types which you usually come across in literature. So one is the block type magnetic skyrmions, which are observed in the bulk systems, where the Dzyalloshinskii-Moriya interaction is due to the non-centrosymmetry of the crystals. So you typically have block type magnetic skyrmions, whereas in thin film multilayer structures, one can introduce artificially Dzyalloshinskii-Moriya interaction. So these are interfacial Dzyalloshinskii-Moriya interaction, which leads to Neal type magnetic skyrmions. So our interest is in looking at the transport behavior and particularly the dynamics, because these skyrmions are seen as a potential candidate for memory devices. And if they are supposed to be in memory device, then one needs to detect them. And detection is, of course, necessary in terms of electrical detection. So therefore, the dynamics is understanding the dynamics is important. So, so this is a typical, Hall effect signal. In a typical Hall effect signal, what one observes a topological Hall effect due to the skyrmion phase. The skyrmion introduces a real space Berry phase as the electron traverses a skyrmion. as you see here. So because of this real space Berry phase, you see that you see a topological Hall effect, which I show here for manganese silicide, where the skyrmion is stabilized in a small temperature regime between 27 to 29 Kelvin. So you see that as the temperature goes up, this topological Hall effect goes away. So similar features have been observed for the room temperature skyrmions also, as I said, for the multi-layer systems, where there is an interfacial Dzyalloshinskii-Moriya interaction. So this group has shown in iridium iron cobalt system, cobalt platinum systems. This is the topological Hall effect feature that the people have reported. And these topological Hall effect are related to the skyrmion density, as they have shown. So our interest is in understanding this topological Hall effect in a different system, and also in addition, we wanted to look at the low frequency dynamics of carriers. So I would like you to note that this topological Hall effect signal is very, very weak, which is of the order of a few tens of nanometer centimeter for both single crystal bulk as well as for multi-layer films. So if you see that, this is around 30-40 nanometer centimeter of that order. So we have, in collaboration with CNRS Thales Research Group, Vincent Cross, we are working on this system. So this is cobalt aluminum platinum system. So this film is prepared by them, and we are performing all the measurements here. So this is a film which we made a few devices out of that film, and this is the magnetization measurement and Hall effect measurement. Now in the Hall effect, typically you will have an ordinary Hall effect and plus an anomalous Hall effect. Anomalous Hall effect consists of these components: scattering, side jump, as well as an intrinsic contribution, that which is also dependent on the magnetization behavior of the system. So now using these parameters, we analyze this data, and we look at the total. We look at the ordinary and anomalous Hall effect. We see that the total Hall effect, there is an additional component. And this we systematically observe in both the upsweep and downsweep curve. Now, if we subtract the anomalous Hall effect from the total Hall effect, this additional component appears as a peak and a dip on the either side of the zero field. So that means when we are downsweeping the field, we see a peak first, a small peak, and then a dip on the other side, and this is repeated when we sweep the other way around. And this is very much reproducible. We have kind of the signal again here is in the similar range of the order of nanometer centimeter. We have measured it at room temperature. And what we'd like you to notice is that in addition to these features, we are also seeing a solder-like behavior which has not been observed or which has not been reported in literature yet. So this is just to show here that these numbers are in the similar regime. And also now if we look at the density, so we wanted to look at the skyrmion density in this system. So we have performed this magnetic force microscopy images. So at different fields, so you see that at zero field, these are mostly, there is no skyrmion, this is worm-like features. That is a perpendicular magnetic anisotropy system. So this is what is expected. And so the corresponding number in the topological Hall effect for the extra Hall effect is here, almost zero. And then as the field progresses, few skyrmions develop here around 80 millitesla, right? Our signal also improves here. And then about 95 millitesla, the density increases further. So the signal is increasing further. And on the lastly, so when it is going to the saturation, the number density is almost decreasing. So here the signal is decreasing. So this extra Hall effect, this is related to skyrmion density. So what we have done is we have calculated the skyrmion density and worm density as a function of field, and we see that there is a peak appearing in the skyrmion density at around 100 millitesla kind of field. So if we plot together with the topological Hall effect or the extra Hall effect, we are a little bit careful at this point because this is just our recent data. We have not yet understood fully. So we are saying extra Hall effect in this case. So this extra Hall effect that we are measuring is has a almost similar field profile as the skyrmion field profile. So we kind of show that this is related to the skyrmion evolution in the system. Now, after we saw that, then we are interested. We are looking at the dynamics of the electrons in this skyrmion phase. So for the dynamics, we have performed noise measurements. So typically, this is what we do. These are the power spectral density in the fluctuations in the voltage, longitudinal voltage, or the longitudinal resistance in the skyrmion phase. So sorry, this is not your skyrmion phase. This is at zero field, and we check this as a function of current to check that to make sure that this noise is coming from the sample. So it is indeed quadratic dependence on the current. So it is showing that it is due to this noise is due to the sample and not due to any extrinsic effect. So now what we did is we performed these measurements as a function of field in the entire entire field range, interesting field range, I would say. And then what we are plotting here is the power spectral density at 1 hertz as a function of field. And if we plot that, we see that there are two peaks appearing in the region where there is the skyrmions are appearing in the system. So in the right side, I am plotting it. I plot the noise along with the skyrmion and worm density, and you see that these two peaks are coming in the region of the skyrmions. Interestingly, the first peak is appearing when the worm density has a very strong slope. So that means here it's in the mixed phase, both worm and skyrmion. This is the first peak that
you have 5 minutes.
Yes. Okay. Right. So this is interesting from the point of view that it shows that the fluctuation is increasing in the skyrmion phase. However, the fluctuation, it is showing a peak also in the worm and skyrmion mixed phase, but it is coming down again in between as the skyrmion is developing. So we are not able to understand the data yet. We are still looking at these data, but we have checked the reproducibility. So these are perfectly reproducible data. And you see that on the right hand side at around 150 millitesla, there is a hump, there is a shoulder kind of feature in the noise again. So this is also not very clear. We are, as I said, we are trying to understand the data. So overall, I would like you to note that in general, the fluctuation is increasing. Fluctuation in the dynamics, the low frequency fluctuation is increasing in the skyrmion phase. Now, to look at how exactly, to look at in more details, what we have done is we have plotted the frequency exponent as a function of field. And what we see is that as the field progresses, the frequency exponent it is going down. Less than 1. So 1 is perfectly 1 by f. So it is less than 1. So less than 1 would mean that the dynamics is faster. And then as the skyrmion phase is fully developed, on the right side, the frequency exponent goes past 1.3. So it is about 1.35, 1.4. And that tells us that the low frequency, the spectral weight towards the lower frequencies is increasing in the skyrmion phase. And so that would mean what it means is that, so I'm plotting it here again along with the noise data. So at the sharpest peak here in the skyrmion phase, we see that the frequency exponent is highest. And that tells us that the low frequency weight is more in the system, and this means that the electrons are slowing down in the skyrmion phase. Okay, so so these are the information that you get from the noise studies. Of course, these skyrmions in this current that we have applied, corresponding to the current density that we have applied, the skyrmions are supposed to be in the static phase. So there is no skyrmion motion as such that we are expecting at this in this current or field regime. So nevertheless, we are seeing this kind of evolution of skyrmion of the charge carrier dynamics, electron dynamics in the skyrmion phase. So yeah, so this is to show you how the noise evolves as a function of field and along with the topological Hall effect or extra Hall effect. So we see that the noise is again, it is following the similar feature, but of course the peak is not at the similar position. But the hump that you see in the topological feature, we are possibly seeing the similar thing in the, I mean, possibly the noise is picking up the same thing here. So we are still looking for an answer to understand this behavior. So I think with this, I would like to summarize. So we have observed an extra Hall effect, which is carrying all the signatures of topological Hall effect that people have reported in literature so far. We are also seeing an additional shoulder, which is a new feature which has not been reported and which is very much reproducible in our system. We see that the fluctuations increase in skyrmion phase, and that is very important from the both from theoretical as well as from practical aspects, because in practical device applications where the transport transport mechanism should be used to detect the skyrmions. So now here we show that for the first time we show that that the skyrmions, I mean that the carriers are actually slowing down in the skyrmion phase. So with this, I would like to thank you for your attention. I'm open for any question.
Yeah, thank you, Pintu, for a nice talk and for keeping the time. And we have time for questions. Yeah, Pratap, you can go ahead.
No, I don't have a question. I'm fine.
Oh, okay, okay.
I have one question. Hi, Pintu. This is Brijesh.
Hi, hello. Yeah, please.
You said somewhere towards the end of your talk that your skyrmion seems to be not moving around or frozen space. Do you have any means, by any means, I mean, have you ascertained whether it is pinned because of impurities or defects, or is it actually forming a reasonable lattice or something? I don't know. I'm any comments on that?
Yeah, so reason I have said that they are not moving is that the critical current density that is required to really move these skyrmions, we are much below that level. Okay, so we have also, of course, not personally, we have not done this experiment to observe the motion, but as we know, the critical current density is of the order of 10 to the power 12 ampere per meter square to really see the skyrmion motion in this.
Just one small query. These plots, I mean, on the three little colorful things, are these real images of the skyrmion arrangement?
Yes.
What are they?
Yes,
Okay.
yes, they are real images. Yes.
And so these red dots are supposed to be skyrmions?
These red dots, yeah, okay, I understand your question. So yeah, these red dots.
So yeah, my question basically is, if you have imaged them, do they look like crystals or they look like disorderly pinned objects? What are they exactly?
Yeah, so these are the real images of the skyrmions. Of course, MFM is not a very good technique to observe skyrmions, but now I think in the community it is kind of considered as a standard imaging tool. I mean, typically Lorentz TEM is used for observing all the details of the skyrmions. But yeah, these are the skyrmions that you observe, and we call it a lattice, but you can see that these are kind of disordered and possibly also pinned at some several locations.
Okay, we will take one quick question. If Manoranjan can go ahead.
Yeah, so nice work and nice presentation. So I have the question related to the last question. You are saying that current is not sufficient, but skyrmion is more like a spin degree of freedom, right? So without even moving the electron, you can move this these spins, right? Because this is more like a spin degree of freedom. So why it is not, I mean, I would expect that it can move without even moving the electrons.
Yeah, so to move skyrmions, you need to give some kind of spin transfer torque into this spin system of such similar things. Like if you consider, for example, domain walls, right? In domain walls, typically the critical current density is much higher than skyrmion. In skyrmion, you can move with much smaller current. But then we have observed actually, or it's also in the literature, that with the small current you can just move them, but in real materials you have pinning centers, right? So they kind of move around. If the current is very small, they kind of move around the pinning centers, and sometimes pinning center, the interaction kind of annihilate.
But you can think in terms of the spin excitations. These are excited modes.
If this discussion can be continued,
I think
in the breakout room,
we can talk later. Yeah.
Yes.
Sure.
There's a nice discussion. I think it can be discussed in the breakout room.
Sure.
In the interest of time.
Okay. Thank you.
Yeah. Sorry. Yes. I think we should move to the next speaker, and thank you, Pintu, and let's thank him for the talk. And I would like to invite the next speaker, Anup Bera from BARC, for his talk. And hi Anup. And he is going to talk on probing quantum phenomena of spin-half antiferromagnet by neutron scattering. So go ahead. You have 25 minutes, and 5 minutes before your talk ends, I will give you a warning.
Okay, thank you, sir, Professor Banerjee.
Yeah, thank you.
My slides are visible?
Yes, perfect.
Okay, good afternoon, everyone. First of all, I would like to thank the organizers for providing me to share my recent results with this community. So today I'll show some quantum phenomena of spin-half 1D antiferromagnets, which are probed by neutron scattering technique. So this is one-dimensional magnet or 1D magnet. It is an old problem. It has started very early last century during the development of the quantum mechanics. And but this problem is still equally fascinating, and day by day we are getting new physics out of these systems. So here this theoretical development started when Professor Ising gave the solution, analytical solution for the 1D Ising chain, and he shows that doesn't order magnetically at finite temperature. Later on, Professor Hans Bethe he gave famous answers and says that for the Heisenberg systems, it also doesn't have magnetic long-range ordering even down to 0 Kelvin. And this Bethe answers and Ising model, they are used extensively for modern condensate systems. And most of the systems we'll see that they are following these theories. But much later on, Professor Halden in 1983, he shows for the first time that even this one-dimensional system or one-dimensional magnet, if we have spin half or integer spin, they are totally different. Their behaviors are totally different. where spin half system is gapless. They have gapless excitation, but spin 1, they show very unique property, which is topologically protected ground state and gap excitation. But this was there are very much advancement on the theory side, but unfortunately the experiment started very late, around 2000, because of unavailability of proper experimental compound what can be studied to verify these theories or to probe the quantum properties of these materials. And this morning, Professor Yusuf has given nice introduction about the low dimensional spin systems, and that make my job easy. So based on these 3-dimensional crystals, one can have different dimensionality. For example, if I take nickel oxide, which is magnetic ion is nickel, and how the nickel ions are arranged in the magnetic lattice, that gives the interaction between the magnetic nickel sides. And if we see the nickel oxide is uniform all over the 3 dimension, and it is 3-dimensional magnet. But if we put a non-magnetic layer like here, so like here, then we make the 2-dimensional lattices of magnetic ions. For example, this is the real compound. If we look on the crystal structure, we see the magnetic, the green layers are magnetic. They are well separated by the non-magnetic gallium layers, and they effectively show 2-dimensional behavior. Similarly, we can get 1-dimensional magnetic magnets based on the real 3-dimensional crystals, where the magnetic ions are arranged in a chain. And today's talk is especially interesting on this 1-dimensional magnet. So what happens really when we go down to lower dimension? Basically, we are reducing the number of exchange bonds. In 3-dimension, there are 6 nearest neighbor. For 2-dimension, that goes down to 4, and 1-dimension goes down to 2. And we have been working on different magnetic materials, mostly based on the oxides, to study their interesting properties. They belong to this kind of dimensionality. But today I will be interested to show the results from the last compound, which is strontium, cobalt to vanadium to OA, which has a spin half. It is not really spin half, but it is a effective spin half that Professor Yusuf explained for the other compound. Due to the spin orbit coupling, the effective spin become half here. And I'll quickly compare the result with the spin on counterpart, which is based on the nickel, and I'll show the experimental proof of the Professor Holden theory. As I said that I will show the results mostly from the Newton scattering experiment. Let's briefly tell about the neutrons. Neutrons are subatomic particles. It has a mass. It doesn't have charge, but it has a spin. But most important for this today's purpose is that it has a dipole moment, which is tiny, but sufficient to probe the magnetic properties of a magnetic system. So it interacts with the matter in 2 ways. It can interact with the nucleus of a element within the crystals, or it can interact with the unpaired spin of an atom, and it gives the information about the magnetic systems. As the Newton can determine the lattice, either nuclear lattice or magnetic lattice. On the other side, it can give energy to the system, or it can take energy from the system and give information about different excitation in the material, like crystal excitation like phonons, or the magnetic excitation, which are known as the magnons, or it can also give other properties of a material. As I said that Newton can interact with the unpaired spin of an atom in the lattice, and if we do the Newton diffraction experiment, we can probe the magnetic lattice, how the spin are aligned in atomic level, either parallel to each other or anti-parallel to each other, or they have different moment size or different complex arrangement that we get from the magnetic crystallography. On the other hand, we know when we have a magnetic system and we disturb this system, and their excitation are magnon or spin waves in the semi-classical physics. So the spin on the spin wave, they are collective excitation, and they form wave-like pattern in the system, and they have a dispersion nature. And by using inelastic Newton scattering, we can measure this dispersion relation very accurately, where the scattering cross section is directly proportional to the dynamic spin-spin correlation. Now come to the today's topic, that quantum phenomena in 1D magnet. So the compound I'll show that shows a one-dimension chain-like crystal structure where the cobalt octahedra, they share edges and form a chain. Okay, this case it is not really stepped, but it shows a skew type of chain, but it is approximately linear. And the chains are well separated by the vanadium O4 tetrahedra. Vanadium is in the 5+ state, so it is a D0, so it doesn't carry any spin. So in my system, it is spin cobalt 2+. There are 7 electrons in the D cell, but I'll show that it effectively becomes spin half. And quick comparison will be given with the nickel compound, which has a 8 electrons in the D cell and carries spin 1. Now, if we do the thermodynamic property measurement like specific heat, immediately we see for the nickel compound, if we go down to 0.3 Kelvin, we don't see any characteristic or anomaly due to the magnetic phase transition. On the other hand, for the cobalt compound, which is a very similar crystal structure, only cobalt ion is different, we do see there is a lambda-like anomaly which corresponding to antiferromagnetic ordering temperature. And the absence of the magnetic ordering for the nickel compound is further confirmed by the Newton diffraction. When we measure Newton diffraction at room temperature and 1.5 Kelvin, we don't see any difference in the pattern. They are identical. There is no contribution from the magnetic lattice. On the other hand, for the cobalt compound, if we measure just above the ordering temperature, which is 5 Kelvin here, we measure at 8 Kelvin and 1.5 Kelvin, we do see the appearance of magnetic BARC peaks, which correspond to the magnetic lattice, order lattice. So if magnetic long range ordering happens for the cobalt compound, for nickel compound, there is no magnetic ordering. Now, as proposed by Professor Halden, the spin 1, which is nickel based compound, it has a topologically protected ground state and there is a gap excitation. Now we measure the excitation by Newton inelastic scattering experiment, which is shown here. And this is the theory, which is the excitation pattern calculated theoretically, which shows there is a presence of energy gap. This is called the Halden gap, and it protects to for the system to order magnetically. And there is nice matching. And how we can understand this behavior, that is the ground state is somehow forming this kind of singlet state, or that is called the valence bond solid state, where the spin 1 quantity of nickel 2+ is decomposed into 2 spin half quantity, and which is entangled with the next nearest neighbor spin. And this is a very entangled state. And when we break one of these bonds, we create one excitation, which is called triplet, and which can be defined by these quantum states, and then we get the excitation. And these excitation are magnon, and they have this dispersion relation. And from this matching, we see that the compound belongs to this Halden state, where this phase diagram is shown as a function of the anisotropy, singular anisotropy, and the interchain coupling. Now you can see if we can increase the interchain coupling, one can drive this system from this Halden state to the order state. That we have shown by 2 ways that we can drive this system to order state. One is already shown by Professor Yusuf, that if we dope the calcium, which has a smaller ionic radius than strontium, we can bring the chains closer to each other, and immediately we can see this is the parent compound. This is susceptibility as a function of temperature. The parent compound doesn't show any peak, but when we substitute some compound, it started showing the peak, which corresponds to the magnetic ordering. And you can see that with concentration, the magnetic ordinary temperature increases. Another way to introduce the long range magnetic ordinary is the application of magnetic field. So when we apply a magnetic field, one of the triplet state goes down and intermixed with the ground state and give you the long range ordinary. Here we have shown that when we apply magnetic field, the Holden state goes through this quantum critical point and show the 3D magnetic ordinary. Indeed, there are other regions which is very interesting, but I am not going today on that direction. Now I'm coming to the compound which is spin half based on the cobalt 2+ ion. As the discussion was that cobalt has a small, it is 3D element, it has a small spin orbit coupling. Yes, if we don't consider the spin orbit coupling due to the crystal field, we know that ground T2G state has a lower energy and EG has a higher energy. So 3 unpaired electrons can be arranged here. But when we introduce the spin orbit coupling, this is energy state is rearranged and the lowest energy state become G effective equal to spin half. And this is experimentally proved by the Newton elastic scattering. So when we do the scattering, we see around 30 milli-electron volt, we see a crystal field excitation. And this excitation, this energy is equivalent to the transition between G effective to G effective 3/2 state. And it gives the confirmation that indeed we have effective spin half. Now I will go to the first example of this quantum phenomena, which is like quark-like confinement in condensed matter. So we know in the high energy physics, the quarks are confined, the single quark cannot be obtained. And I will show based on this compound that similar phenomena we can have in a condensed matter system based on the spin half 1D magnet. Like quick overview of the quark confinement. In the mesons or baryons like neutron, proton, they are formed with the quarks, and quarks are always exist in pairs. So if we want to pull them out, we'll see after certain range, instead of becoming individual quark, there will be quark pair will be created and we'll basically get new mesons, but never will get this individual quark. This is well known in the quantum chromodynamics in the high energy physics, and it's known as a quark confinement. And if we look on the potential energy for this quark separation, we see that when the separation is little higher, it shows a linear increase of the potential as we increase the distance between these quarks. Now I come to my system on the spin half chain compound. Now this is shown as a function of temperature susceptibility data. So when we cool the system, since it is a topology is one dimension, it does go to the low 3-dimensional magnetic ordinary, and before that higher temperature it goes to a state which is known as the 1D magnetic state, which experimentally confirmed from the Newton diffraction study. So this is the magnetic diffraction pattern at different temperature. If we go down, we see there is a broad diffuse scattering appearing in the diffraction pattern due to the 1-dimensional magnetic arrangement. And then at low temperature, when the 3-dimensional magnetic starts in, we see the magnetic Bragg peaks. Now, here I have shown the inelastic pattern here, which shows a very broad and diffuse type of behavior, which is very much in contrast with the excitation for the previous compound based on the nickel. So nickel case, we say that we know that magnetic excitations are magnon. They are spin 1 quasi-particle, and they have very well-defined dispersion relations. But we don't see in the case of cobalt compound, which is spin half. So what exactly happening here? These magnons are decomposing into 2 quasi-particles, and each of them carrying spin half. And since there are 2 quasi-particles, and in Newton inelastic scattering experiment, we see the change of spin 1. So we are basically seeing the combined effect of these 2 quasi-particles. So the combined effect gives us this continuum kind of behavior. So this decomposition of the magnon is a purely quantum phenomena, and it is fractional quasi-particles. They are prime attention for the quantum spin liquid system. So this is the story for when we are at the above the nil temperature, we are about at 6 Kelvin. Now, this dispersion or this distribution of the intensity, which exactly can be calculated from the Bethe answers, and they see there is a nice agreement between them. This experimental measure intensity and the intensity calculated from the original Bethe's theory for this Hamiltonian, we see there is a nice agreement. And from there, we calculated the interaction between the spins is around 7 electron volt, and there is an anisotropy. This anisotropy is the single ion anisotropy, and this anisotropy in the system. Now, if we go below the ordering temperature in the 3D order state at 1.5 Kelvin, we are adding one more term, which is the coupling between the chains. So immediately we see this the broad or diffuse, this continuum state is not no more continuum. It become nicely this excited state with many like energy states, which appear due to the confinement of the spin-on pair. So if I take a cut here, I see this nice energy states which is going up. And for this case, we see a broad behavior. Now, how do we can understand this phenomena? So it is shown again the same thing. So when we are at higher temperature above the magnetic ordering, by flipping one spin, we create two excited quasi-particles which are known as spin-on. Now we can move this spin-on without any costing any additional energy, because if I flip one spin and three spin, they cause equal energy. And due these spin-ons are free to move along this chain, and then that's why we are getting that continuum. But as soon as we go below the ordering temperature, the chains are not free now. They are coupled to the nearer chain. So there is a interchain coupling. Now, if I want to move them apart, then we have to break this exchange interaction between the chain, and which provides the potential for the confinement of the quasi-particles. So this interchain coupling effectively providing the potential for the confinement. And then we, as soon as we break this thing 1, 2, 3 bonds, we get these energy states. So this is the confinement of spin. Now we can also measure the center of mass motion of the spin-on pairs, which can be defined by the one-dimensional Schrodinger equation. Here is the potential, and this is the energy state. Now, if we solve this energy state like this, which is 2E0. E0 is basically energy to create the first, flip the first spin to create two spin-on, and then this is the energy required to separate them out. This is basically the negative zeros of the array function. And if I plot this energy of this or eigenstate of this eigenenergies of these states as a function of the negative 0 of the array function,
you have 5 minutes.
Okay, so it's showing a linear behavior. So it shows that there is a linear potential, and which is very much equal to the quark confinement. So it proves that we see the quark-like confinement in the condensed matter system. Now I'm coming to the other quantum phenomena that we have recently observed in this system, which is Bethe string, and which is first proposed initially by Professor Bethe. He says that in certain conditions, the spin excitation can interact with each other and they will form kind of string. And if we switch on the magnetic field in this system, we see that we can suppress this nil order and we can go to quantum critical state. And in this quantum critical state, the spin are continuously fluctuating, but if a certain time, if I take the snapshot, we see that this is the ground state. And from there, we can see different kind of excitation, where 3 spin can be confined, string or 2 string or single type of excitation that we have observed in the spin 0 state. And they have different kind of spectral weight in the system. Now, when by doing the Newton elastic experiment, we measure the excitation under magnetic field in the QMAT21 state, and we see that this is the theoretical excitation pattern here. Here this is the shown by the 2 string states, and this is for the 3 string state. And we see their variation with the magnetic field. We see that this is the 3 string state which has different mass than the others, and which has a higher mass, and 2 string state we see how it varies with the magnetic field, and we see this is a different mass, and which has been proved by several experiments. Indeed, these are the string state. Further, we continue to look how they vary this string state up to the saturation magnetic field by terahertz spectroscopy, which comes around 28 Tesla. Now we see these 2 string and 3 string state, they disappear at high field, and rather the low energy that excitation, they become magnon when it saturates, which is expected for a spin or the ferromagnet. So this I comes to the summary. So I have shown basically 2 phenomena, quantum phenomena, based on the spin half chain compound. First one is the in zero field, but we observe the spinon, quark-like confinement of the spinons, which is effectively governed by the interchain coupling. And then we see the under field when we go to the quantum critical state, we see there is a presence of string state, and we experimentally proved the string state for the first time, which was not observed for the century. The prediction was done in 1931, and over the century it was not observed, and we are the first time our group experimentally proved that indeed this kind of string state present in spin half chain compound. And I like to the pupil, especially Professor Yusuf, for his encouragement and support for this work, and my postdoc supervisor, Professor Bera, and the different pupil involvement for this several Neutron scattering experiment or for the theory and crystal growth. Thank you very much. Thank you for your kind attention.
Thank you, Anup. Thank you for the nice talk. So now the session is open for questions. Yeah, Pratap.
Anup, that was a nice talk. If we can go to your last slide where you show the 2 phase diagrams.
Yeah, here.
Yeah.
Yes.
So you mentioned this state as the quantum critical state.
Yes.
But where is the quantum critical point here?
Okay.
From which the state comes.
Yes, I agree. So because as I presented in zero field, that this is a compound which has a weak interchain coupling, and weak interchain coupling basically does not lead to the quantum critical state. Instead, we see the order state at very low temperature, but at higher temperature it is in the critical state, means the spins are not order, but they are highly interacting spins. So,
yes, but that could be thermal. That could be a thermally fluctuating state.
Yes, I can show you, because this experiment, this result, what I have shown here, they are basically measured at 50 millikelvin, even within this order state. But still we see this kind of quantum, there is no ordering, because this ordering, they are partial ordering of the spins, and they don't affect the high energy excitation or high energy physics of this compound. They only change something very low energies and they stabilize this state. But there is very weak thermal fluctuation effect in this. But basically, these are the quantum effect, because this state we observe when we apply magnetic field. So it is totally driven by the magnetic field, not by the thermal energy.
Okay, thank you.
Yeah, welcome.
Okay. I have one question that in this free spin-on state, this 1D state where you see the the dispersion is sort of like a continuum.
Yeah, continuum.
You don't explore the full K space, because on one side you have explored up to this and up to 3.
Yeah, actually this will be, as I show you, the theoretical source, there is a symmetry.
Yes,
And due
yes.
to the geometrical restriction of the instrument, we could not
Oh, I see.
derive. But it
I
will
see.
be the symmetry. You can see up to this point, it is very symmetric. And this theory also says it is symmetric about this zone center.
Okay,
So,
okay.
so it is understandable that other side will come similar way. So we can go to some Q point here, but
Okay.
due to geometrical constant, we cannot measure experimentally.
And one other very interesting results, but where is the confinement when you introduce the coupling between the strings? I mean, between those 1D chains, where is the coupling? You know, you said there is a linear sort of a potential, confining potential, which gives rise to these quantized states. Where is that coming from?
Yeah, that is basically coming from, because experimentally you do see the energy eigen states.
Right, you see the quantized state, yeah.
Yeah, so they have certain energies.
Yes.
Now, if I solve this center of mass of this pinon pair, which is basically can be defined by the one-dimensional Schrodinger equation.
I understood that. I wanted to know the confining potential. You have used the linear this triangular sort of a.
Yes. So this, if I solve it, the energy, eigen energy, we get like this. This is after solving this. And you can see it has two terms. One is the E0. E0 basically energy required to first create the spin-on pair. And this term govern the, when we separate them one by one, so we get this term. And if I show this, the blue points, it has from the experimental energy, and it is plotted as a function of this xi j, which is the negative zero job, and it shows a linear behavior. So this is my energy state, and this linear behavior corresponding to the linear energy potential. So this is the distance between the spin-on. So if we increase the distance between the spin-on, we see the energy required to separate them out, it is increasing linear.
I see. Okay. Manoranjan, a quick question.
Sorry.
Yeah, Anupji, thank you for the nice talk. I have one question. You have showed CV plot for the spin half system. There you see that this lambda kind of behavior, right?
Yeah.
So why is that?
Okay, so as I say that this is not perfectly spin-on chain. These chains are coupled by weak interaction. And this weak interaction leads to the 3D magnetic ordering. And when the 3D magnetic ordering happens, we get this corresponding anomaly in the specific heat.
But in a spin half chain, generally, if you have a like a distortion or the dimerization in the system, then also you get this kind of behavior. A spin chiral kind of transition, if you get, then also you get this thing. But corresponding to this CV, you should have a chi where this gap should be. You can see the gaps. Okay, actually, so I don't know whether you have that.
No. Actually, I can show you this. If we do this Neutron diffraction, I can directly show that there are peak brackets. Okay, I have not shown the magnetic structure here. Basically, this is a linear chain, and we are getting the anti-parallel alignment of the spins. So it is like a nil state we are getting.
I see.
Because of the weak interchain coupling, which is forcing the system to order. And if I go back to the my phase diagram, I show you here that we can. So we are here in the zero field. So this is the perfectly 1D state. What you are saying, that what is expected for a perfect 1D chain, spin half chain, that we see in the above 5 Kelvin, but below 5 Kelvin, we see the nil antiferromagnetic state is stabilized. But this state is not very strong. We can apply a magnetic field and we can go to the, we can destroy this state because the interchain couplings are weak.
Okay, thank you.
Yeah, in the interest of time, I'm sure there are many more questions. You can write directly to Anup on the chat box, or
I'll be there to answer your queries.
To answer the queries, or you can meet him in the breakout room and ask him to come to the breakout room. So we will continue with the next talk, which is the 15 minutes last talk of the session, which is Sanat Ghosh, and he will have 15 minutes.
Yeah, can you hear me?
Yes.
Yeah, let me share my screen.
So 5 minutes before your end of your talk, I will give you a warning.
Sure. So shall I start?
Yeah, sure. Go ahead.
Yeah.
Sanat,
So
Sanat, can you open up your video?
Yeah, sure.
Yeah,
can you see me now? Yeah.
Go on.
So hi everyone, my name is Sanat Ghosh. I am a PhD student working in the nanoelectronics group in TIFR under Professor Mandar Deshmukh. So I'll be talking about some of our recent studies on photoresponse of ITC superconducting nanowires. So I mean the main message that I want to give is that we have figured out a way to make nanowires of ITC superconducting material, and shown that this can be used as a sensitive bolometer. Now before going to the main study, so let me ask the question, why these superconducting nanowires are interesting. So as I already mentioned that people have shown that these nanowires can be used as a bolometer, and it has been reached to single photon limit also. So apart from that, so recently it has been also shown that in nanowires one can get a quantized energy level, and this quantized energy, because of this quantized energy level, one can replace these nanowires with Josephson junction, which people use in quantum measurement circuits. And another important work in work, it has been shown that these nanowires can be also act as a nonlinear inductor for qubit systems. Now with this in mind, so let's ask what are the possible ways that one can make superconducting nanowires. So there are a few possible ways. So for example, so for example, people have shown that one can sputter superconducting material on a carbon nanotube template to get superconducting nanowires. And if one has a planar structure, then one can define nanowire by ion milling or physical etching out. And in some cases, it has also been.
Hello? You share your screen. Your screen is not here.
Yeah, your screen sharing has stopped.
I see. Sorry. Share screen.
Yeah, good.
Can I see it now?
Yes.
Yeah. So so in some cases, it has also been shown that when high energetic ion beam is irradiated on a surface of planar superconductor, this can also locally destroy its superconductivity, and this could be another possible way to make superconducting nanowires. Now, when we want to make superconducting nanowires from a planar structure by this method, so difficulties can arise. For example, this procedure of physical etching or ion irradiation can cause inhomogeneity and disorder in the system. Now, to circumvent this issue, what we have done that we have figured out a way to make superconducting nanowire in a different way. So the main idea behind is that, so the system that we use is QMAT superconductor BISCO, which is a high TC superconductor, and this is a van der Waals material and can be exfoliated like graphene. So this cartoon shows the main the message is that when we deposit chromium on the surface of a thin layer of BISCO, chromium makes the underneath BISCO insulator. So we have done the transport and the spectroscopy study to show this behavior. And so, I mean, if we use this technique, so one can define the nanowire by simply depositing two chromium lines with a gap in between them, and this gap defines the nanowire geometry. So I will not go too much in the details of the process. The details is shown in this manuscript. Now, before going to the device result, let me briefly tell you how we make these nanowires. So as I mentioned, this BISCO is a van der Waals material and can be exfoliated like we exfoliate graphene. So usually we exfoliate graphene by or other 2D materials by Scotch tape technique. Instead, here we use a different technique called anodic bonding method. So the reason for using this anodic bonding method is that by this way we can get a large area of thin layers of BISCO, and the procedure is as follows. So we as a substrate, we take a special glass substrate which has sodium ion doped in it, and we place a bulk crystal of BISCO and heat the total assembly. So when we heat it, so the sodium ion gets mobile in the glass substrate, and then those can move in the glass. And so after that we apply a very high voltage across the BISCO and the glass. So what happens is that because of this large electric field, the sodium ions can move to one of the surface, and because of this image charge forms at the BISCO crystal, and that electrostatically gets bonded the first few layer of BISCO. And then we peel off the bulk from the substrate with the usual Scotch tape, and we get thin layers of BISCO. And after that, we make contacts with the BISCO flake by shadow mask evaporation. So we don't do any chemical processing of the system, as it is known that this degrades the quality of the superconductor. So we align a mask with the flake and then deposit metal contacts. So I will mainly focus on nanowires that we make by this method, which has a length of 30 micron and 700 nanometer width. So the measurement, we first do electrical characterization, and the measurement schematic is shown cartoonly here. So where we simultaneously measure the response across the nanowire and also the pristine BISCO, to make sure that during the fabrication steps the BISCO is intact or of good quality. So first we do this 4-probe measurement of resistance versus temperature. Now you see two scales here. The left scale shows the resistance versus temperature of the nanowire, and the right scale shows the resistance versus temperature of the BISCO. Now the blue curve that is shown here, it has two parts. So if you see the electrode geometry, so you can clearly see that this involves the superconducting nanowire plus some part of the extended flake. So and we get the pure nanowire response once the extended flake has gone superconducting. So then whatever response you see is coming from the superconducting nanowire, and we define the nanowire normal state resistance at the temperature where the bulk part has gone superconducting. Now then we measured the bias dependent resistance. So this is a differential resistance of the nanowire as a function of biasing current. And what we see is there are two things to note here. So one is there are hysteresis in upsweep and downsweep of the current direction, and there are multiple peaks in the DVDI when it goes from superconducting to normal state. Now the hysteresis that we see can be understood by the hotspot model explained by Tinkham, where there is the consideration is that there is a normal spot on the nanowire, and that dissipates heat, and because of heating effect you get hysteresis. Now to see why there are multiple peaks in the DVDI, we next ask the question, what is the mechanism when current is driven through a superconductor, and what is the mechanism by which it becomes normal? So the so the idea is that when you pass a high current through your superconductor, it gives kinetic energy to your Cooper pairs, and when the kinetic energy exceeds beyond the pair breaking energy, then the superconductor
You have
can
5
go
minutes.
okay, sorry, from superconductor to normal state. And but when you have a reduced dimension, for example, in 1D system, when the width of the nanowire is less than the superconducting coherence length and the magnetic tension depth, then the dissipation can also occur in terms of phase slip centers, where along the length of the nanowire, some part momentarily becomes normal and start dissipating. A similar situation occurs in 2D system also, where where the width of the nanowire is larger than the lambda and the xi, where resistive vortex motion can happen, and the 2D analog of phase slip center, which is phase slip line, can start dissipating in your system. Now, a typical identity of this phase slip center or phase slip line occurs in the IV characteristics, where you have the multiple jumps from the superconducting to normal state. And we, in our device, we similarly see this kind of behavior, which seems to suggest that the phase slip line can be a mechanism by which the superconductor becomes normal. Now, to visualize this, next what we do is measure the photoresponse of the nanowire. So for that, what we do is we shine laser on the nanowire, and its intensity is modulated at some frequency, and we measure the photovoltage generated across the nanowire at the same frequency. So here you see simultaneously measured differential resistance and the photovoltage across the nanowire. And then what we do is we park the nanowire at specific biasing current, and then map out the photovoltage, spatially mapping of the photovoltage. And what we see is that there is a maximum photovoltage at the middle of the nanowire at this biasing current. And when we change the biasing current to different current value, this photovoltage maximum point seems to move along the nanowire. And to for one-to-one correspondence of this mapping, what we simultaneously do is map out the reflection image from the device. So the dotted box that you see is the chromium line boundary, and the gap between the two box is the nanowire region. So the summary from till this is that whatever we see in the multiple peaks as a DVDI data, so this seems to suggest that there are phase slip lines along the nanowire which moves as you change the biasing current. Then what we do this photovoltage measurement at different temperatures and calculate what is the responsivity, which is a benchmark for how good is a bolometer. So this responsivity is defined as the generated photovoltage by laser power, and this shows that this is a decent bolometer and comparable to the existing ones. Now, next, what we do is we make another superconducting nanowires of 3 micron length and 300 nanometer wide. And in that case, what we found out is that there is only one photovoltage spot along the nanowire, and there are no resistive transition from superconducting to normal state, as we see for a longer nanowire. And so the reason behind this, why we don't see this multiple phase, I mean, the phase slips events here is not very clear to us for now. But apart from the two length scale that I already said, the coherence length and the magnetic penetration depth, there is another important length scale here in this problem, which is thermal healing length.
You have very little less time. So
yeah, I'm about to finish it. Yeah. So which is about 1.5 to 2 micrometer length, and since the nanowire that I show here is a length of similar value, we don't see these multiple hotspots of the photovoltage. So with this, let me summarize. So what we have shown that we have figured out a way to make superconducting nanowires of high temperature superconductor, and shown that this can be used as a sensitive bolometer. And we show that for longer nanowire, there are phase slip lines driven superconducting to normal state transition, and we image those spots where the photovoltage is maximum along the nanowire length, and those spots change to move position when you change the biasing current. Whereas in shorter version of the nanowire, we don't see such behavior. So with this, so let me thank and yeah. So if you have any question, you can ask.
Yeah, thank you, Sanat, for a nice talk. And we have, since we are over time, we have time for just some 1 or 2 very quick questions. So Souvik can go ahead. Yeah.
Hi, Sanat. It's a great talk. So I have 2 questions really. One is that is there any intrinsic advantage of using BISCO for these?
So, yeah, right. So thanks for asking the question.
How thin can be your nanowire with this technique?
Yeah. So thanks for asking the question. So the advantage of using BISCO is that first of all the nanowires that is there as a bolometer, they are of low TC. So to operate those, you have to go to very low temperature, possibly with liquid helium. And the advantage of using BISCO is that it has a TC of 85 Kelvin. So you can use a detector which can operate at liquid nitrogen temperature. The another question that you ask is what is the current limitation of, so what we have found is that till now we could achieve a nanowire of width of 300 nanometer. But we believe that this can be pushed down to even lower limit if we take some extra steps.
Okay, great. So no other advantage other than the high TC that you can think
no.
of? Okay.
Yeah, and so another thing is that so these are van der Waals material, so you can make detectors of extremely small form factor. So if you can go to a monolayer limit, that can be a extra sensitive bolometer.
Okay, great. Thanks. Yeah.
Okay. If any further questions? One quick question. I was just curious. What is the response time? Do you know how fast these systems can respond?
Yeah, so that is a good question. So we have not measured the response time from the nanowire device. Yeah.
Okay. Thank you. So I think thank you for everyone for a very exciting set of talks and for this session, and for everyone keeping roughly the time. And so I now hand it over to the organizer.
Thank you, Satyajit,
Thank
you. Chairing this session and maintaining the time. So we'll have now the lunch break. The next session will be from 2:30. As usual, the session will be open 10 minutes in advance. And the link is given in the program that I shared with everyone again this morning. So each session has a different link. This link will not work for the next session. You have to go to the program and click on the correct link. Okay, so see you at 2:30.